Great pleasure to welcome Yara over from California to give the last talk of the workshop. So, yeah, the Yara's, as you see, goes first about singularity structure or gravity amplitudes, maybe black holes.
Black holes, not yet. Yeah. Okay, thanks a lot, organizers, for the invitation for a very nice workshop. So, the motivation of the talk is to take some of the mathematical structures we saw in the planar n=4 super Young mills, and I will review some of them briefly, and try to generalize it or try to see what can be the possible generalization in other theories. And in the first step, it will go to the non-planar, or the full n=4 Young mills theory, and then to n=8 supergravity. So the plan of the talk is exactly that. So first I review briefly what are on-shell diagrams and amplituhedron in the context of planar n=4. I then say something of what are the ideas, how that can extend beyond the planar limit, because this everything is formulated in the planar limit of n=4. And then what we learned recently about supergravity, on-shell diagrams and amplitudes. But the main question really behind everything is if the loop integrand beyond the planar limit makes a good sense. We know that in the planar limit, the loop integrand is unique, it's very nice, and everybody likes that. It has special properties, it's very rigidly fixed by certain assumptions. But in the non-planar case, there are some major problems corresponding to the absence of global variables beyond the planar limit. And the integrand is not unique, and the question is if there is any interesting structure there. Okay, but let's start. So I'm interested in the scattering amplitudes for massless particles in 4 dimensions, and mostly in the context of loop amplitudes in this talk. And well, we can expand the full amplitude as a sum of integrals or Feynman diagrams that we have to integrate over the loop momenta. But in the planar sector, it also makes sense, or it makes sense in general, but in the planar sector, you can uniquely sum these things and define the integrand as one object that then should be integrated. And the general idea is that both the integrand and the full amplitude is fixed from singularities. But while this is a rational function, this is some complicated transcendental function. So here, this function has some complicated branch cut structure, and we don't really know how to characterize it and how to specify what the function is, and we don't even know the function space at higher loops. But this function is a rational function, and it has poles, and we can say where the poles are, and we can calculate the residues on these poles. So this function, which I will also call integrand, is an ideal object to study and construct, having in mind that if you are interested in the final amplitudes, you have to integrate in the end. Now, the integrand, there are 2 statements about the integrand. We can do physical statements we can formulate kinematically. One is the statement about the locality of the theory, which corresponds just to the presence of 1/p² poles in the integrand, and the other statement is the unitarity, which says that the integrand factorizes on the poles either the 3-level factorization or something called forward limit, or for the loop integrand we can also sit on 2 poles, and then this is the famous unitarity cut. Now we can iteratively use these cut equations and factorize the full loop integrand in the products of trees. So cuts of loops are products of trees. And if you cut everything you can, you get maximal cuts. But now, if we further factorize even that picture, because these maximal cut pictures have still 3-level amplitudes in the corners, so you can further factorize 3-level amplitudes using recursion relations until you get on-shell diagrams. So then I will discuss the on-shell diagrams. So on-shell diagrams, if you think about it from the other side, are based on gluing together 3-point amplitudes. So there are fundamental 3-point amplitudes in n=4 super Young mills. These are expressions of the full 3-point superamplitudes corresponding to the two solutions of on-shell 3-point momentum, on-shell 3-point kinematics. And these are the expressions for the 3-point amplitudes, but now I replace these expressions by just these pictures. But these 3-point amplitudes exist also in many other theories, like gravity and so on. All theories with fundamental 3-point vertices, we can define the 3-point amplitudes. There are always two of them. Now, of course, for the real kinematics, the 3-point amplitudes are 0 because the 3-point kinematics forces the momenta to be complex in the 3-point case. But we can take these building blocks, having in mind that these are complex expressions, and glue them together, and we get objects like that, when each picture just represents the product of 3-point amplitudes in the corners. That's the definition of the picture. And we are summing or integrating over the space of particles that can propagate in the middle. In the maximally supersymmetric theories, we are just summing over all multiplet, and that's it. Now, know that these pictures, based on the unitarity methods, are also cuts of loop integrants. So this is, for example, the quadruple cut of the 4.1 loop integrand. This is an octacut of the 2-loop 5-point integrand, and so on. So these are also the maximal cut pictures of the loop integrands. Now, we define this function by the product of 3-point amplitudes, and we just get some function of external kinematics. And in the case when the number of internal propagators is bigger than 4 times L, where L is the number of internal loops in the picture, we get some extra delta functions, like this picture. This picture doesn't have any loops, but has one propagator. These two guys are 3-point on-shell amplitudes, which means that S12 is equal to 0. So this is the 4-point 3-level amplitude on a factorization channel, on an S channel. Now, this picture, which I showed before, has exactly 4 internal lines at one loop. It means that the loop momentum is completely localized by 4 on-shell conditions, and this is just a rational function of external kinematics. While this last picture, when the number of propagators is less than 4L, there is one unfixed parameter, I call it Z, so this is a function of one parameter. And this is an heptacut of the 2-loop 4-point amplitude, so there is one parameter left. We cut it only 7 propagators, so the 8 degrees of freedom in 2 loop momenta, there is one left. Now, the surprising statement is that these diagrams, they represent cuts of loops, but they can be also used in the planar n equals 4 as building blocks for the integrands directly. And it's done by the BCFW recursion relations and its generalization to loop integrand. And there is some recursive procedure how to expand the full loop integrand in terms of these on-shell diagrams. This is kind of the 3-level part. It's basically integrating this equation for what are the singularities of the loop integrand. This corresponds to the forward limit term. This corresponds to the 3-level factorization. And this extra structure on top of these terms corresponds to BCFW shift, written in terms of on-shell diagrams. Now, the representation of the amplitude we get is very different from what we would get if we use the standard expansion in terms of diagrams. In the simplest case of 4.1 loop, where the planar n equals 4k amplitude has only one diagram, there is also only one on-shell diagram, which looks like that. It's actually 5-loop on-shell diagram, but it has 16 internal propagators, which fixes 16 out of 20 degrees of freedom in this diagram, leaving 4 degrees of freedom left, which are exactly identified with the off-shell loop momentum. But for more complicated cases, we get on-shell diagrams which don't have any interpretation, like the standard integrals. And the reason is that, like in the 3-level case, when the BCFW produces non-local representation of the 3-level amplitudes, the same thing is true at loop level, and the on-shell diagrams are non-local. They don't have Feynman propagators in general. They have spurious poles that cancel once we sum over all of them. Okay. Now, there is a connection between these diagrams and some interesting mathematical structures corresponding to the Grassmannian. And there are many ways how to motivate the connection, but the simplest one is thinking about the momentum conservation for spinor helicity variables. So if we use the usual momenta, the momentum conservation is just the linear condition on external momenta. If we use planar helicity variables, it's a quadratic condition. And now it's a natural question, can we linearize the quadratic condition as the two sets of linear conditions? So now these C and D matrices are matrices of coefficients. So this is a linear equations for lambda tilde and linear equations for lambda. And indeed, we can. And this C matrix, the matrix of coefficients, and the D matrix are actually related. And they form the Grassmannian matrix, which is just K by N matrix modulo GLK. And it describes geometrically a K-plane in N dimensions. This C matrix of these has many free coefficients, because this momentum conservation can be linearized in many different ways. And the interesting thing is that each on-shell diagram gives us one of these C matrices. So for example, this simplest on-shell diagram, which looks like that, gives us, using some procedure of defining variables corresponding either to faces in the diagram or edges, there is a rule how to give the C matrix as parameterized using these variables. And this C matrix then linearizes the momentum conservation for the diagram as a set of linear conditions. Now, there is a further connection this is true actually for all diagrams. They don't have to be planar, they can be non-planar. But in the planar case, if you declare that these variables are positive, then also all the minors of this matrix are positive. And then the Grassmannian is called positive Grassmannian. And then there is a very interesting connection to the algebraic geometry and combinatorics, which connection between these graphs and permutations and stratifications of this positive Grassmannian. Well, I will not talk about it in details today. Now, interesting connection to physics, to this mathematical picture, which might look interesting, but why does it have anything to do with the definition of on-shell diagrams as products of 3-point amplitudes? That's not obvious. But the same function as a product of 3-point amplitudes can be actually obtained from these variables of the C matrix, and this is the formula for this case. You just take the simple form in all the variables that parameterize the matrix, d alpha over alpha, and then you get some delta function c dot z, where c dot z is exactly this linearized momentum conservation, c dot lambda tilde, then the other C matrix dot lambda, and then in case of supersymmetric theories, there are also some fermionic variables. So this is a completely different formula for the same object, which naively doesn't know anything about 3-point amplitudes, anything about n equals 4 super Young Mills, and so on, but this is what the formula is for n equals 4 super Young Mills. And you can prove it actually recursively that this is correct. Now, from physics point of view, each on-shell diagram has manifest dual conformal symmetry and also the Youngian symmetry. And this can be translated into the diffeomorphisms on this positive Grassmannian space. So it's some property of the C matrix. It's a property of the geometry. And the other statement for each on-shell diagram is that all singularities are logarithmic. The logarithmic singularity means that if I go close to the pole, for example, alpha 1 goes to 0, the function behaves like d alpha over alpha, or the form behaves like d alpha over alpha. We will talk about it more later, what are the implications. Now, because we have the recursion relation for the integrand in terms of on-shell diagrams, this is also true for the final integrand for the amplitude, because it's true term by term. And I would like to stress here that all the dependence on kinematics in each diagram is really pushed into this delta function, just into the momentum conservation. So the momentum conservation becomes crucial for the connection to the kinematics and the real world, but everything else is going on in this abstract Grassmannian space. So the physics is kind of removed, and the mathematical structures become manifest here, or become important. But the question is, so here, these recursion relations, despite they use these on-shell diagrams, they still rely on the unitarity. Because the recursion relations is just implementation of the unitarity, telling us what are the factorization channels of amplitudes and which we have to sum. So there is a question, which on-shell diagrams do we have to sum? And the answer is, well, there are recursion relations which tell us which diagrams we have to sum. So if there is some complete geometric picture for the full thing where the physics is completely removed and the mathematics becomes the dominant one, we should also remove this last step. And that's what we did with NEMA a few years ago. And this kind of combines all on-shell diagrams together and giving purely mathematical definition for what the amplitude is. And there was an early work, there is a typo of Andrew Hodges, who found some very simple example of NMHV tree-level amplitudes when you can associate the BCFW terms directly with the volumes of tetrahedra in momentum twistor space. And he found that the amplitude corresponds to the polyhedron, while different BCFW recursions corresponds to different triangulations of this polyhedron. But it took a number of years to generalize this picture, because this picture doesn't stay in the projective space where this original Andrew's finding was formulated, but it goes to this Grassmannian space. Okay. Now more about these logarithmic singularities. So I keep talking about logarithmic singularities. So again, it means that if we go to a pole in some parameterization where x goes to 0, the function behaves like, or the form behaves like dx over x. So, and this is the statement about the poles in the cut structure. Now, you can think that this is kind of trivial because all poles are single poles in the loop integrands, but this is a statement about all the cuts, not just about the first poles, but if you cut more propagators at the same time. And the example where the form has simple poles, but it doesn't have logarithmic singularities is that one, dx dy over xy x plus y. If you sit on the residue x is 0, this thing becomes dy over y squared. So it doesn't have logarithmic singularities, despite it has single poles. But it seems to be a defining property of n equals 4 super Yang-Mills, that all the singularities are logarithmic. So this is the property of on-shell diagram. This is an input in this amplituhedron picture. And because we know that it's true for on-shell diagrams and there exists recursion, it's actually the correct property. And also certain integrals can be written in that representation. So for example, this is just the 4.1 loop box integral written in the usual momentum representation form. There exists a change of variables from L, from 4 components of L into some functions f1, f2, f3, and f4, such that the box integral just looks like that. And for example, f1 is L square over L minus L star square, where L star is the solution to the quadruple cut. Okay. Now, now we know that the integrands of loop amplitudes are fixed by cuts. So this is the statement about unitarity methods, that if you write some ansatz, you check enough number of cuts, you fully specify the amplitude. So from this point of view, it's a unique object specified by cuts. Now, if we are in the planar sector and we are using global variables, we can actually list all the solutions for the cuts in these global variables and just make this list, and that specifies the answer. If we say what are the residues on the given solutions of cuts. Now, from the practical point of view, what the amplituhedron provides is the complete set of these cuts to all loop orders. It just gives us where all the cuts are and what are the residues on these cuts. And it gives us in the form of inequalities. So we parameterize the loop momenta using some parameters, and there are some inequalities. If these inequalities are violated, this is an illegal cut. If they are satisfied, it's a legal cut. So this is in practice. Of course, the picture contains a little more, because then it takes these inequalities and says that they define a region in the Grassmannian. So this is on top of that. So this is some geometry on top of that. But from the point of view of cuts, this is exactly what the picture gives you. And this is non-trivial that you can do it to all loop orders, because just drawing on possible on-shell diagrams and saying what all the cuts are to all loop orders, it's an infinite complexity question if you go to arbitrary loops. But in planar n equals 4, there is a compact solution to it, and that's these equations, so you can write them down. Of course, there is a non-trivial work to take these equations and build the object. You just know what all the constraints are. It's not a constructive procedure of telling you how to build the object, but you know all the constraints to all loop orders that fully specify the object. So that's what the picture is. Well, as I said, in addition, there is the statement that these inequalities, well, if you have a set of inequalities, it's very natural to ask, do they specify some region in some space? And indeed, they do, in that case.
You know, they're not all inconsistent.
What? Yeah.
Is there a signature in the
They can, well, it can be empty, yeah. So, yeah, here we know that, yeah, it's non-empty space, yeah. Well, it is empty, for example, for some helicity violating amplitudes. If you take k equals 1 amplitude for n point, you would get an empty space, yeah.
Can you give an example of an illegal cut? Well, like what's
Well, so there are two types of illegal cuts. The one type is that, because if you talk about the integrand as one object, and you forget the diagrams as the expansion, you can think about putting everything in their common denominator. Your one function as an integrand. So of course, if you start to do cuts which don't correspond to diagrams, it's illegal. Yeah,
okay.
You cut something. That's one type. There is the other type which says that, for example, if you are doing MHV amplitudes, there are solutions to the cuts which correspond to diagrams, which don't have MHV support. They have, for example, NMHV support or MHV bar. So this is the other set of illegal cuts. Yeah, the first set of illegal cuts, which I wanted to discuss, are actually poles at infinity, which are cuts which don't really cut propagators. They send the momentum to infinity. So it's a different set of cuts, and they are also illegal. So they are incompatible with these equations, but we actually know that in n equals 4 these cuts cannot happen because they are related to the dual conformal symmetry. The fact that you can formulate the integrand in momentum twistor space without any introducing of momentum infinity twister means that there are no poles at infinity. So whenever in the cut structure you send L to infinity, it's forbidden. That's forbidden cut. And in the end, I will also discuss the link to the UV behavior. There is obviously a link to the UV behavior because the way how we normally check the UV property is just the power counting, sending L to infinity. But there is more in it, just that. And so, for example, the bubble integral at one loop obviously has a pole at infinity. I just take L and send it to infinity, and it has a pole. And that's UV divergent. Of course, there are other cases, like the triangle integral, which also has this pole, but not directly. I cannot sell L to infinity here. I wouldn't find any pole. But if I first do the triple cut on the triangle, cut 3 propagators, I get one parametric function, 1 degree of freedom left, and I can choose this degree of freedom to parameterize L in a linear way as L equals alpha lambda 1 lambda 2 tilde, and it's d alpha over alpha. So sending alpha to infinity sends L to infinity. So it has a pole at infinity also. So this never happens in n equals 4. We know that the triangles don't show up. So the fact that the triangles don't show up and the triangle subdiagrams at higher loops is one concrete consequence, but it's actually more than that. You can have also box subdiagrams which still have poles at infinity and they cannot show up because of this property as well. Okay, so there is the other statement which follows from these inequalities, and because it's inequalities with the 0 on the right hand side, you can actually interpret the legal cuts also. You can interpret the inequalities in the following way. So there is actually some non-trivial step. I will not really go to it because it's a relation between the amplituhedron and the dual amplituhedron that Nima often discusses. But in the end, the statement that it's a geometric space with inequalities says that there shouldn't be any source terms. So I have a function, I have this integrand form, and the question is which cuts I have to check in order to fully specify it. And the fact that it corresponds to these inequalities is closely related to the fact that the only cuts I have to check are the ones where the integrand vanishes. So in other words, once I specify where it must vanish, I fully fix the form. So I will never use, I don't have to use, I can, but I don't have to use directly unitarity cuts or these pictures where the cut of the integrand gives some non-zero function. I can only use where the cut is 0. Yeah? And once I satisfy all these zeros, I fix everything up to an overall constant. So I refer to it as homogeneous conditions. So that's the planar story. Now, quickly, what we learned in last 2 years for the non-planar case, and that will open the gates to the gravity. So the non-planar problem, there is principal problem from just from the beginning when you start to think about non-planar amplitudes in this particular direction, and that's the absence of global variables and unique integrand. So even at one loop in n equals 4, you have 3 box integrals, and it's not clear what is your L, because any choice of L in one diagram is incompatible with choices of L in the other diagram. So if you want to sum these 3 boxes, it's not really a well-defined operation. And consequently to that, there are no momentum twisters, and also there is no dual conformal symmetry or Youngian or no known symmetries of that type. But the on-shell diagram still exists, so I can just draw the diagram like that and define it as a product of 3-point amplitudes, and it will be cut off loops because the non-planar integrands still factorize into products of trees on the cuts. That's all the same. But there is no recursion relations which would take these diagrams and build the integrand itself. We don't know what it is, and exactly the problem is because we don't know what the labels are. So, but one can still study these diagrams, and these diagrams are very similar to the planar sector. So again, all these singularities are logarithmic in the diagrams, and again, all the kinematics is in the delta function. There is some difference that it doesn't correspond to this positive Grassmannian anymore, but it's just some subspace in the full Grassmannian. But that's irrelevant for the talk today. But the logarithmics are the singularities are still logarithmic, so it's a natural conjecture to say that if there exists recursion relation using these diagrams, because they have logarithmic singularities, then the full amplitude also should have this property. So we can make this conjecture, and we can just test it directly on the amplitude. And okay, so this is the full set of conjectures. In addition to the logarithmic singularities, we can also mimic the planar findings and ask if there are poles at infinity in the cut structure, and also if the full amplitude, now in the context of the diagrams, we don't have any other objects at the moment to expand it, is fixed by these homogeneous cuts. And this is what it would correspond to, or what does it correspond to on the planar side. So if this is true, this would say that it might be volume of something. We would know what the region is or in which space it lives, but the fact that the singularities are logarithmic defines some natural volume form. The no poles at infinity in the planar sector correspond to dual conformal symmetry. So if this is still true, there would be an evidence for something beyond the planar sector of that type. And these homogeneous cuts corresponded to these scattering equations, to the fact that we can compactly write some conditions to sequence of cuts we have to satisfy, but in a way which doesn't have any source terms. We don't need to know what are the lower loop, lower point amplitude, how does it factorize. We just specify where it vanishes, and that's all. And there is another extra step to say that these inequalities actually define something geometrically. So here the setup is just to use the standard expansion of the amplitude using diagrams like that at 2 loop 4 point, color factors, and some coefficients which should be fixed. And in our context, we want to fix them only by zeros, by these homogeneous conditions. And the basis of integrals we build in a way which satisfies these first 2 properties term by term. Know that, for example, in this 2-loop case, some diagrams like this one are forbidden just from scratch, because this diagram actually violates these 2 properties, so it cannot be there. And you can do it at 2-loop 4 point, 2-loop 5 point, 3-loop 4 point. That's how far we got with, because it's difficult to construct these terms. So there is there are other representations of these amplitudes in the literature, of course, but they don't exhibit these properties. They exhibit other properties like VCJ, and this seems not compatible with each other. The amplitude is the only object which has all of that. You have to choose what you want to make manifest in. any particular representation. But indeed, if you construct these bases and you try to fix these coefficients with these homogeneous conditions, you will be successful. So that's the lesson, that the non-planar amplitudes behave like the planar ones, at least for these checks which mimic the properties of the planar amplitude. So there seems to be no difference. There is no single property of the planar amplitude which doesn't go to the non-planar. Of course, it cannot be formulated in the symmetry language. We don't have momentum twistors dual conformal symmetry, but the consequences are there. So I would say that n equals 4 is the full, not just planar, is the simplest QFT. Now the open question is if you can actually formulate it as symmetries. Now, what is the role of color factors? Because I was completely blind of writing here the color factors and not doing anything with that, but they are extremely important, and if there is some geometric story and so on, it must be included in a critical way. I don't have any ideas what to do with that. And I think that once the role of color factors is resolved, that might say what the possible geometry is behind it. But it's just evidence. It must be found explicitly, these things. Okay, but despite we haven't resolved the non-planar story completely, we can still move on at that stage and look at gravity and what is interesting there. Okay, so when one talks about Yang-Mills square and the double copy, 3-point amplitudes of gravity are exactly squares of Yang-Mills. So that's the point where everything squares perfectly. Unfortunately, for the on-shell diagrams, which are products of 3-point amplitudes, it's not direct square, because there are some Jacobian factors from solving these cut equations. But the equation is that the GR times phi cube, which for 3-point is just 1, is Yang-Mills square. But the phi cube, so we have the Yang-Mills expressions. They have these logarithmic singularities and some nice properties. Unfortunately, well, you can still say something if you square them, so the things are meaningful, but the phi cube completely changes the way how the gravity on-shell diagrams behave. Yeah? The phi cube just changes everything. So unfortunately, here we cannot, it seems that the Yang-Mills properties doesn't really carry over to gravity. They are completely different, except one I will mention in a second, when actually the BCJ relations can be used to prove something very interesting at this level. Okay, but let's just start with generating some data. So we can just try to calculate the on-shell diagrams just as products of 3-point amplitudes and to see how the gravity on-shell diagrams, how do they look like. So this is actually a 4.1 loop cut. In Yang-Mills, it's just given by the Park-Taylor formula. In that case, it's actually also 4.3 level amplitude. In gravity, it looks like that. Some formula. You see that it's not holomorphic anymore. It has these anti-holomorphic things. But we know that the gravity doesn't satisfy these holomorphic properties as the MHV Yang-Mills. Now you calculate this one with this expression. Looks still pretty nice. This one. So, and then you make some conjecture after a few examples. And the natural conjecture for this case of this type of diagrams would be that in the numerator you get anti-holomorphic pieces, as you saw all here, and the denominator you get single poles. There were no double poles, just single poles with holomorphic brackets. And then you go to the first other diagram, and you find that there is some double pole. Okay, so one of the conjectures was wrong. But then also you see that the numerator contains some mixed brackets, so it contains both holomorphic and anti-holomorphic. Okay, so the numerators are more complicated and there are higher poles in the denominator. So it doesn't seem very exciting. Yeah, it looks like more generic expressions, but then you have to go look at the details, what exactly the numerators and denominators mean here. So the first statement is that the double poles and other triple poles, you can actually get arbitrary orders of poles in the denominator, corresponds to the poles at infinity. So whenever you sit on one of these poles, you actually probe some singularity of the diagram when the momentum flow in one of the legs is 0. So this removes this leg. So this is the edge removal, which was already one feature of the Yang-Mills on-shell diagrams. But if you sit on the pole which is to multiple power, it doesn't set any propagator to 0. Exactly the opposite. It sets the loop momentum in one of the loops to infinity. So it's a pole at infinity. It probes the singularity where L goes to infinity. In the numerator, these factors, which might look complicated, the important thing is that the full numerator factorizes as the product in all cases. And each factor you can actually interpret as some collinearity condition in the vertices of the diagrams. So whenever the free momenta in a given vertex are collinear, the diagram vanishes. So this is how the numerator is constructed. So there are two things, poles at infinity and collinearity conditions in the numerator. So, but this is just inspecting the diagrams based on definition, the way how we calculate them is just product of 3-point amplitudes, just from the physics definition. But while there is an actual question how we can embed them in this Grassmannian formalism. So even in the simplest case, we draw the same diagram, we use the same procedure to build this C-matrix. And in the Young-Mills, in the n equals 4 super Young-Mills, the diagram was calculated by this formula using these variables. The question is, does there exist any formula like that for the gravity? And the answer is yes. The formula looks different. It has higher poles in the denominator in these variables, and it has some factors for each of the vertex. So it looks different, but this formula exists for all diagrams. And inspecting this formula more, you see that there are higher poles, but whenever the alpha goes to 0, actually corresponds to a singularity at finite loop momentum location. The numerator kills 2 of the powers, and it becomes a single pole. But whenever it corresponds, the alpha goes to 0, or corresponds to L goes to infinity, it stays there. And actually, the numerator can even add another factors of that. So you can get arbitrary orders in the end. And also, the diagram vanishes explicitly when any of these deltas are 0. And the delta is 0 is this collinearity condition in the vertex. And the similar formula you can also derive for any number of supersymmetries. There is just some extra factor you multiply it. It's exactly the same as for people that know what was it in n equals 4 super Young-Mill generalization to n less than 4 Young-Mills. Now there is a relation to the work by Paul Heslop and Arthur Lipstein, who actually at the same time we were looking at these diagrams, they also look at these diagrams with the little different motivation, because they were interested in the BCFW tree-level recursion. We were more interested in the thinking about diagrams at cuts of the loops and what does it mean for the loop integrands. But in the BCFW tree-level recursion, there is a big difference between the Young-Mills and gravity, because while in Young-Mills, the tree-level amplitude is just a sum of on-shell diagrams. In Young-Mills, in gravity, there are extra 1/s factors at each step in the recursion. This just corresponds to the fact that if you do the BCFW shift in gravity, you have 1/s factor whenever you do the shift. Yeah, so this just carries over. So therefore, if you remember from the Arthur's talk from yesterday, there were these 1/s factor everywhere in the recursion, and they calculated them and embedded in this Grassmannian language as well. Okay, but so this is one part. So the on-shell diagrams exist, and we can calculate them using Grassmannian. That's nice. But now we would like to see what we can learn about the gravity loop integrands from that. And because we don't have any recursion relations for loops, we cannot directly carry over these things that are true for the on-shell diagrams to amplitudes. Yeah? Because we don't know how to express the amplitudes in terms of diagrams. But we can still make optimistic conjectures that it's just true. Yeah? So whatever was true for on-shell diagrams, it's true for gravity, and we can test it. And there were these 3 properties. The first of them were these logarithmic poles. Whenever the pole was at finite location in the loop momentum space. But there were also poles at infinity of arbitrary degree. And there were these collinearity conditions whenever free on-shell momenta were collinear in the cut, the full thing vanished. These two properties corresponds to IR, because this is probing the cuts and this is probing some collinearity, while the pole at infinity corresponds to the UV of the amplitude. So now the first statement, you can actually almost prove that it's true. So at the level of on-shell diagrams, it means that whenever we cut, we have some integral, amplitude or not amplitude, and we do cut, the alpha over alpha square, this never happens. Yeah? If we do the normal cuts and cutting the propagators. So this never happens for Young-Mills, and now the conjecture is based on this knowledge, based on this Grassmannian formula for on-shell diagrams, that this never happens for the gravity amplitudes as well. And you can actually almost prove it from the BCJ, making two different assumptions. The first assumption, so first we write the Young-Mills amplitude first in the BCJ form, so the numerators which satisfy BCJ, but then we also write it in this D-log form. By that I mean that this corresponds to the diagrams which manifestly have only these logarithmic singularities. Now the assumption is that there always exist local BCJ numerators, and that there always exists this D-log representation of amplitude. So there is no counterexample at the moment for both of the assumptions. So I just proceed with them. So if it is true, you just take this double copy. And because the only double poles that can happen are from these denominators, and this ND-log already is the row of ND-log is cancelled, the double poles that can be generated by the S's, which are products of the Sij's and others. Adding another factor doesn't spoil anything. Yeah. If it doesn't have any extra poles, if it has extra poles, then the proof doesn't go through. But if it is just a polynomial in the numerator, it's just proven that these poles are logarithmic. So okay, so this might sound like some curious property, but it actually has a direct implications. So perhaps there are new implications if we go to more complicated examples, but we can interpret things that are known directly in this language. For example, as I said, in the Young-Mills expansion, this diagram at 2 loop 4 point was not present, and it was not present because of these double poles. And if it is true for gravity, it's not present as well. And there are some little complicated arguments which say why this is not there in 2-loop gravity amplitude, but this just directly says this diagram has double poles, it shouldn't be in the gravity amplitudes. And actually there exists a whole family of the diagrams like that which have critical divergence, the dimension where they diverge in 4 plus 4L. So they are exactly below the Young-Mills critical dimension, and they are forbidden also in gravity. Okay, it's like 10 to the minus 6 evidence that because this type of diagrams are not there, that the gravity should always stay above this critical dimension. Because if the argument corresponds is somehow related to double poles, at least partially, why the worse behaved diagrams cannot be there, then it both applies in Young-Mills and gravity. Okay, now the other are the collinearity conditions. And to be precise, it means that whenever we have some on-shell diagram, so anything can be in this gray zone, any vertices and propagators, but whenever we have some 3-point subdiagram, then this means that L1, L2, and L3, the lambda tildes are all proportional. Sorry, the lambdas of them are all proportional, but it means that these on-shell diagrams have to always generate L1, L2 in the numerator. And if we have this type of cut, it must generate this guy in the numerator. In the special case, it actually corresponds to the collinear limit of the gravity amplitudes. When if we set the angle bracket 1, 2 to 0 in numerator, there is generated a square bracket. But this is more general, yeah, because here there are only external kinematics. I'm saying that these L1, L2 can be both external and internal. So it's a generalization of this statement to the cuts of the loops, and the on-shell diagrams say that it's still true. And just to show that this is a non-trivial condition even at 1 loop 4 point, and there is no way how to implement it in the diagrams. So here we can consider the double cut two propagators L and L minus P1, and consider the solution for L, which looks like lambda 1 and some lambda L tilde. And now the statement says that this diagram, or this cut of the amplitude, must generate L1 in the numerator. If you do it for the three diagrams in the 4.1 loop expansion, each diagram gives 1 over L1. You sum three of them, and it gives 1. So it violates the conjecture. But then you realize that you chose some variables here. You chose what your L is in some special way. Well, there are actually two choices. The L is either going in one or going the other way. So there are two different distinct choices. If you consider the other choice and you sum now over all 6 diagrams, so 3 plus 3, you actually generate this factor in the numerator. So the symmetrization is very important here, and actually the two-loop check is even more impressive, that there is completely massive cancellation between all the diagrams all together in different labels. You have to consider everything to actually exhibit this property. And this is also, this fact that the symmetrization is crucial is also related to the, I think it's closely related to this pre-integrand story by JJ. And somehow you have to symmetrize in order to see these properties of the integrands. Okay, so both these properties, logarithmic poles and collinearity, tell us something about the IR. Now, the logarithmic poles basically say that the cuts are well defined at all levels. So whenever you cut, you always find a pole, so you can take the residue on the pole. You never find this d alpha over alpha square. The question is if this is captured by some geometry, this sequence of cuts. Now, these collinearity conditions actually are directly related to the good IR behavior of the gravity. The one-loop check at 4 point I showed you, the fact that it behaved like that in this collinear region is actually directly responsible to the fact that the one-loop amplitude behaves like 1 over epsilon in dimensional regularization and not like 1 over epsilon square as the Young-Mills. Yeah. There is actually a direct consequence, you can see. And it seems that this integrand statement is actually even stronger. Yeah. So maybe you can say even something more than just that. Yeah. Which would be interesting if you can make some stronger IR statements. Okay, but the main problem, which I will just comment and not resolve, is about the UV. And as we know, there is the problem with the UV divergences and equals to supergravity. The calculations are not at the moment there to answer that question. And as probably all of you know, it should start just by power counting at 7 loops, where this diagram and many other diagrams are just power counting divergent. And if there is some improved UV behavior, there must be cancellations between these diagrams. And well, if yes, the most interesting question is, for me, it's not if yes or no, but if yes, then why? And if no, what are the details? Why no? Now, the general goal would be to explore these UV properties, not just UV divergences, but in general the UV of gravity at the level of integrand. Because here you have to first integrate, then put everything together and to see if it cancels. So, of course, the ideal situation would be to first explore at the level of integrand without any integration and to make argument why it's one way or the other way. So let me so let me say more about the poles at infinity in this context. So the pole at infinity for L goes to infinity, the normal power counting check is just L sending to alpha L and then sending alpha to infinity. So in this context, for example, the bubble is just behaves like that, and it has a pole at infinity, while the triangle is not of the same form because you first have to cut. You have to first little bit go to the IR, you have to go to the cut, and then go to infinity. So when we talk about the power counting UV divergence or pole at infinity, we normally mean that, just collectively scale all the loop momenta and send them to infinity. But the pole at infinity can be there also here. While this one directly corresponds to UV divergence, this one doesn't. And the reason is that this pole at infinity happens in the complex plane, not in the real plane. because here L is alpha lambda 1 lambda 2 tilde, so this is already a complex momentum. So there is a pole at infinity, but when we integrate over the real slice, it's not in the integration domain. So therefore the triangle is fine, but the bubble is not fine, because there is actually a pole in the integration domain. Now, in n equals 8 supergravity, there are poles at infinity on the cuts. So for example, and they start at free loops. So if we consider the maximal cut of the free loop 4-point amplitude, it's a 10 cut. So there are 2 free parameters, but I just display one of them. It behaves like dz over z, where z just parameterizes, linearly parameterizes momentum in the diagram. And that's a pole at infinity. And there is nothing to do about it. This is not a statement of diagrams and representation. There is just a flat pole at infinity. This is a cut of the amplitude. So however you represent it, the pole is there. And at higher loops, there are higher poles. From this point of view, there is nothing special at 7. It just starts at 3 and it gets worse every loop order. But generically, everything is complex. You can actually show that this pole at infinity happens only in the complex plane. Yeah? Because as I said, in order to see the poles at infinity, you first have to cut, and that moves you to the complex plane, and now the pole at infinity becomes harmless. But there is this balance. Do you go sufficiently far in order to be harmless or not? Yeah, but that's exactly the main question. Yeah, this is impossible just to, at the moment, answer on general grounds. But in order to have better understanding, we need some general argument when this transition happens. Yeah, between real and complex, and when the pole at infinity kicks in. And I think, so that's my speculation, if we actually understand some analog of these scattering equations, not even thinking about embedding them geometrically, it should answer exactly that question. Because in the planar n equals 4 case, it told us where all the poles are, including poles at infinity, which were absent, so there were not. But if we know where all the poles are in the gravity amplitudes, and they are somehow compactly defined, then we can answer that question. Are they real or complex? Do they correspond to UV divergent, or they don't? And the other thing is that if you think about it from the diagrammatic expansion, then if the result is UV finite, it needs cancellation between diagrams. But we already saw this cancellation in IR. This 4.1 loop example in IR, we needed all diagrams, even with all possible labels, to sum them in order to exhibit the IR behavior. So from this point of view, it's encouraging that this already happens in the simple case in IR, so why not in UV? Yeah, but that's just a heuristic argument. Now, independent on this UV question, for me, the most pressing question is what is special about n equals 8. Yeah? So maybe it's the UV or some detailed structure of UV, but in which sense n equals 8 is the simplest quantum field theory. And I strongly believe that, or I hope, that it's some rigidity of the structure of poles at infinity, because the IR is somehow trivial, and all the Jews are in these poles at infinity. So if the n equals 8 is somehow rigid and unique, I think this is exactly where this will manifest. Okay, thank you.
Questions?
So, to what extent does this hold relies on? To what extent will, if there is a divergence at 7 loops or whatever,
Yeah.
it's going to be due to some operators that are not protected by supersymmetry somehow. So, to what extent does the whole formalism, can the whole formalism capture this?
Well, here we exactly, yeah, but here the point is that we are playing exactly the opposite game. We don't know anything about Lagrangian, we don't know anything about that. We are trying to see what are the defining structure of amplitudes. In Young-Mills we can do it, and we don't know anything about the Young-Mills part. We don't know what the rules of the games are for the gravity.
You assume something like supersymmetry. I mean, it must rely very strongly on supersymmetry.
Well, it has n equals 8 supersymmetry. That's true, but it's no consequences are used of n equals 8 supersymmetry. The supersymmetry is completely kind of pushed into these delta functions. Yeah. So it's like in n equals 4. If you go lower, you will have extra factors. Yeah. So the results will be different. That's true. But
Okay, can you actually use this formalism to compute amplitudes in n equal 2 Young-Mills, for instance? Or?
yes, you can.
Okay.
Well, it's in n equals 2. Actually, you can. Yeah. Well, it's just the question of existence of these recursion relations. The diagrams exist for any number of supersymmetries. The question is, can you put them together to build the amplitude? And you can in n equals 4. You can in n equals 2. There are some problems with these forward limit terms because they are divergent and you have to regulate them. Some people recently were interested in that question. So yeah, in principle you can, but from this point of view, these theories are not so rigid. We don't know. If you forget all this stuff, if you just say, I want a rational function, which is my integrand, and this is a set of properties that defines the function. We know it only for n equals 4. For n equals 2, 1, 0, we can use recursion relations, but that's not, this is not how you would define mathematically the function. Yeah, some recursive definition, glue things together, shift, and so on. So it's a prescription, but it's not a defining property of the function. Yeah.
But presumably you're okay in constructing loop integrands in the planar case. It's just the non-planar case where you're stuck.
Yeah, in the non-planar case, you actually, so this is like, this is the message. In the non-planar case, we know all the conditions, but it's not formulated in the good variables. Yeah.
Oh.
So you cannot just write down the function because which variables do you use? Yeah.
There's no trick. There's no BCJ trick you can use to build up the planar.
Yeah, I know. Nobody convinced me that there is any trick how to avoid this variable problem. Yeah.
Yeah,
So
in fact, I mean, you can get to a multiple loop level where you need non-planar information to generate everything.
I see. There would be gaps if you tried to.
Yeah, if you just started
build
from planar,
everything out of planar.
you wouldn't capture it. You wouldn't capture the entire level.
yeah.
That's a shame. Well, maybe not. Maybe that's a bit true. Any other questions? Let's thank Yara again for the presentation.